Okay, today we're going to start looking at the area of physics called special relativity. So when we've been looking at how things move, the motion of objects, we base them on principles of relativity. So if we say we've got a car moving, we are basing our analysis of that motion based on a fixed point. So say we're observing this car moving from this point, and the velocity is the velocity with regard to this fixed point. The distance is regard to this fixed point here. But say we are sitting in the car, you're inside the car, then you're not experiencing, you're not actually moving, you're sitting still. And it looks as if now this person is moving away from you, and that is the distance from your point. So the way that you perceive motion depends, our perception of motion is determined by our frame of reference. So the concepts of displacement, velocity, and acceleration, as we understand them, may then be developed as a position in space measured from an origin. So for this, the car moving, there's our origin, the wee person observing it. A rate of change of position, so that would be velocity. And a rate of change of velocity, and that is acceleration. This is all referred to as Newtonian relativity or dynamics. So everything we've learnt so far comes under the heading of Newtonian dynamics, and we apply Newton's laws of motion to these systems. Now, Newton worked in the late 1600s. A further concept known as invariance was developed by early physicists such as both Newton but also Galileo. And this assumed that laws established in the laboratory held true universally. And were not dependent on where or how they were measured. Or if the observer was in motion. This became known as Galilean invariance. For example, an experiment done in a lab on land would provide the same results as one carried out in a lab on the hold of a ship at sea, which was sailing steadily across the Atlantic. Now, with these concepts, low velocity motions were studied and the laws of motion with which we are familiar were established. So the low velocities, the laws of motion were established. So we took all the laws of motion that Newton came up with, and all those different motion equations that we have. They were done. Experiments were done. They were repeated in different situations, and they were found to be true and to hold. Most importantly, Newtonian relativity leads us to the concept of the frame of reference. So the frame of reference. The frame of reference is identified by the origin. So this is what is identified by the origin or fixed reference point. As humans, we tend to put ourselves at the central and defining point of all motion. For example, if we throw a ball, the ball is moving away from me. I am stationary. Even though, so if we think about, we throw a ball, oops, there's our ball, we've thrown our ball, and we say we are stationary, the ball is motion. But let's think about it, are we truly stationary? We are standing on the surface of a planet that's spinning about its own axis, and this planet that we're on is spinning very quickly round the sun, and this sun is spinning round, there's our wee sun there, is spinning round a galaxy. So when we're standing throwing our ball, we are definitely not stationary. But because our frame of we're looking at the frame of reference, that on the surface of the earth we throw our ball, to our frame of reference we are stationary. So that's what is important when we think about our frame of reference. And when we're dealing, up to this point, when we've dealt with our Newtonian dynamics, we've not really had to put too much thought into it. But when we come into the sphere of special relativity, frames of reference become very, very important. Let's look at this a bit more closely. So we've got a car, and you're in this car, and you're going at this direction, and your velocity is 70 miles per hour. You're on the motorway. You're driving at 70 miles per hour. I'll put 60 miles an hour. Okay. Now, a car's coming towards you in the opposite direction on the other side of the motorway, and that car is also driving at 60 miles per hour. Now we see at the side of the road there's a policeman, and he has a radar gun, and he points the radar gun at your car, and he sees you're coming towards him at 60 miles an hour. He points the radar gun in the opposite direction, and he sees this car coming towards you at 60 miles an hour. If you, here, you're in your car here, you see the policeman coming towards you at 60 miles an hour, because you are in your frame of reference, which is inside the car, and he is outside your frame of reference, and it appears for him to be coming towards you. Now, if you look at this car coming towards you, you're driving in this direction at 60, the car's coming towards you at 60, the car moving towards you appears to be travelling at 120 miles per hour, because you've got the 60 of your speed, the 60 of their speed, and they come together and appear to be 120. Now, what if you overtake another car? I'm just going to draw it here, it would be in the wrong lane. Here, and this car is driving at 50 miles per hour. It's going to look, if next time you're on the motorway, look at the cars coming towards you in the opposite direction, opposite carriageway. It'll look like they're driving really, really quickly. When you overtake a car, it looks like the car that you're overtaking is actually going slower. So it's going to look like this car to you is only going at 10 miles per hour, because the difference in your velocities is 10 miles per hour, that they're relative to each other, because you're observing this car from your frame of reference. And so you can see how your frame of reference is really important. And this is all applying Newtonian dynamics to this situation. Now, towards the end of the 1800s, James Clerk Maxwell was working on electromagnetism. And interestingly, the electromagnetism cast doubt on Newtonian relativity. Maxwell concluded that light is an electromagnetic wave. And Maxwell concluded that the speed of light is constant. And we can calculate, and is defined by two universal constants. So Maxwell found that the speed of light c is equal to 1 over the square root of this number epsilon times mu, where epsilon is the permittivity of free space, and mu is the permeability of free space. Now, we're not going to go into what these actually mean just now, but these are two universal constants that are parameters in which the universe operates. And if you they're fixed, if you take these two numbers, you multiply them together, square root them, and then inverse them, you will find the speed of light. So therefore, the speed of light is itself a universal constant. Therefore, it must be constant regardless of the frame of reference. It's a constant in every frame of reference. And because of the Galilean invariance, this must hold true for all frames of reference. Now, fast forward a few years to Einstein. He performed thought experiments. At his time, some of his experiments they wouldn't be easy to do in a laboratory, so he would think these experiments out and what would be the result of them. So this is one of his thought of experiments. Imagine you are, so let's this is a variation of his thought. One of his famous thought experiments was that he was sitting on a tram, sorry, and on his way to work, and at the end of the street there was a big clock, and he imagined what would happen if he was travelling in his tram close to the speed of light. What would the time look like on that clock? And he was thinking about the way the light coming off the clock, and as it came to him, how would him travelling at the speed of light affect the time that he would see on the clock. And this got him to thinking. So let's look again at our travelling on the road, on the motorway, and this time we've got our policeman here, and he's got his radar gun to take our speed, but this time we're travelling at half the speed of light. But this time, instead of measuring our car speed, we've got our headlights here, and he is going to measure the speed of the light waves coming off our headlights. So according to Newtonian dynamics, the speed would be 1.5 times the speed of light. But that can't be, because the speed of light cannot exceed c, so this would violate what Maxwell discovered, so we have a problem. Who's correct? Is Newtonian dynamics correct, or was Maxwell correct and the speed of light does not exceed c? Einstein postulated that the speed of light does not change, but instead the time and the length of between the frames of the reference is what varies. So it's the nature of space and time for a moving object are changed relative to a stationary observer, which is a very profound and quite a strange thought when we come to see the implications of this. So let's consider Einstein's thought experiment. So we've got a light clock, which is simply a pair of parallel mirrors. So we've got mirror 1 and mirror 2. And we put a light beam, and the light beam comes up here and hits this mirror here, then it bounces back down to here. And we can measure the distance as equal to the speed, which is c, times the time that it takes to go up and then back down. And this is our light beam. Now imagine the two mirrors are travelling at a velocity. So we take this whole setup and we move it at some velocity. An observer moving with the mirrors would discern no difference. So say we put these mirrors onto a train, and we're sat on the train and we've got our two mirrors and the light beams bouncing between them as the train trundles along, we would still observe this. But now imagine that you're not on the train, you're on the platform. And we have mirror 1, and we're going to take our light beam and we're going to emit it, and but at the same time the train is moving in this direction with some velocity. So by time that it hits mirror 2 is now over here. So the light beam appears to have went in this direction. So this is mirror 2. Now the beam of light bounces off mirror 2, and by time it gets back to mirror 1, it appears that mirror 1 is over here. So just think about, you're standing on the platform observing this, mirror 1's here, and imagine taking a picture of a very, very fast framed camera. Picture. Mirror 1's going to be here, and then it's going to look like mirror 2's over here. Take new pictures and it's going to look like mirror 1 is moved over here, because this whole mirror setup, this light clock, is on this moving train. And so we now have the setup where this is our distance that we had up here, CT. Now this distance here is going to be the time travelled in the time t, whilst it's moving at some velocity v. So this is vt. And this is the time that of the journey. And then this distance here by Pythagoras, this distance here is going to be the time ct dash. So now we're going to apply Pythagoras to this. Ct dash squared is going to be ct squared plus v dashed squared, and then t dashed squared will be t squared plus vt dashed over c all squared. So we've just divided through by c, and if we work through rearranging all that, we will come to this equation. T dashed is equal to t times 1 over 1 minus v over c squared, where t is the observed time of the stationary observer, so that's the wee man here watching this light clock moving on this very fast train. T is the observed time of the moving observer. So remember, our light clock's on the train, and imagine you're sitting on the train with your light clock. It's going to be the same time you would measure as you were doing it here when it wasn't on a train. And the velocity v is the velocity of object, so the speed that the train's going in this situation, and c is the speed of light, and we measure the velocity in meters per second, and the time is going to be in seconds for both of them. Now, let's just going to rewrite this here. So remember, t dashed is the observed time of a stationary observer, t then times 1 over 1 minus v over c squared. Now this here is called the Lorentz factor. And we give it the symbol gamma. This shows us that the time they measure is different by this scaling factor, so that the observer on the train and the observer on the platform will see time differently. And we can rewrite this as just t dashed is t times gamma. In other words, the observed time elapsing is longer than the time experienced in a moving frame of reference. Therefore, when measuring or predicting motions of fast-moving objects, stationary objects must correct the time effects of time dilation. So this is called time dilation. Now, an interesting little thought experiment. Imagine we're in the future, here's Earth, and we blast a spaceship off to do some mission far, far away. And we've got the technology that the spaceship is going to move close to the speed of light and it's going to come back. Now imagine the person on the spaceship is on the spaceship for 10 years. So this little person on the spaceship is going away for 10 years off to space, to the far reaches of the solar system, and beyond, out into outer space on whatever mission, and then the spaceship comes back after 10 years. On Earth, so the people that the astronaut knew on Earth will be significantly older than our spaceship. Say that the spaceship travels at 0.95 the speed of light. For 10 years away, the people on Earth will be 50 years older. So if that person was 40 when they left on the spaceship, in their time of when they're on their mission, they'll have their 50th birthday. But the people on Earth, they'll be 90. A 40-year-old on Earth will now be 90 when that spaceship comes back. Time dilation is a very weird thing, and yeah, very weird thing. And we'll look at some scientific some results to prove it in a minute. But let's just if we graph the Lorentz factor, and we graph the velocity over c, and if we have 1 here, so that's where if the velocity was the speed of light, and here's 1, we have this happening. And if we do 1 over, so the dotted line is 1 over gamma, and this the proper line is just gamma. So what we can see is when we are when we've got low velocities, the Lorentz factor doesn't really make any difference, and so Newtonian dynamics play a part. So as v gets beyond about 10% of c, then the Lorentz factor begins to rise. and we need to start taking it into account. So that's how time is affected as we at high velocities. We're now going to look at length contraction. So, similar thought experiment is we're going to have two mirrors, and say we're just sitting beside our two mirrors, and our beam of light goes out that way and then bounces back and comes here. So this is a stationary distance equal to L. Now, imagine we observe, we put our little setup on our train again, we let the light come out, it's going to leave our first mirror, and so we're observing this from our platform, this is on our train, this is observed, and then this mirror is not going to be here anymore, it's going to be moved over here, and our light beam comes here, so this is going at velocity v. The distance will be, now where was it, this is where it would be originally, will be equal to L dashed plus velocity times t1, and then when it bounces back to here, but this mirror is now going to be in a different location because it's moving, and it moves back to here, and the distance here will be equal to L dashed minus v2, not v2, velocity is still the same, t2. So the time for this whole, when it's stationary, the time for, this is L here, will be 2 times L over c. We know that from time dilation, the time of this for the stationary observer is going to be t times 1 over 1 minus v over c squared. But we know that t is equal to this. So I'm going to continue working up here. So t dashed is going to be equal to, so we're going to substitute in for 2L over c. 1 minus v squared over c squared, and we're going to call this equation 1. A stationary observer outside the train also sees the mirrors constantly moving to the right. So we've got our t1 is the time from this position to this position. And so that in that time it's going to, this mirror is going for, is the distance that this mirror goes here is v t1. And hence the distance that so if we've got a wee photon here, what distance does this photon travel? So it's going to say d1 is ct1 equal to vt1 plus L dash. So this is the length observed by the stationary observer. And we know t1 is the length observed by the stationary observer over c minus v. Oops, that's not a c. On its return journey, I'll write t2 over here. This is the time that the mirror goes from this mirror, jumps off here and comes back to here. The left mirror then approaches at a distance of VT2 before, this is VT2, sorry, before it hits it, and that's VT1. So T2 is going to be the length divided by C plus V. So T dashed is equal to T1 plus T2, the 2 times from leaving this mirror to here, then from leaving this mirror to here. So that's L dashed over C is a C there, minus V plus L dashed over C plus V. And then we can rearrange that to get 2L dashed over C divided by 1 minus V over C squared, and we'll call that equation 2. So this has to be equal to this. And if we rearrange it all, I'm just going to write the result down, we get L dashed equal to L 1 minus V over C squared, or L dashed is equal to L times the Lorentz factor, where L dashed is the observed length by a stationary observer. L is the observed length by the moving observer and the velocity is the velocity of the, for example, the train, and c is the speed of light. And again, meters, length is in meters and velocity is in meters per second. Now, when this was first, so what does this mean? Length measured by a stationary observer, i.e. length dash, L dashed, is shorter than length measured by an observer in the moving frame of reference. Therefore, when measuring or predicting the motions of fast-moving objects, stationary observers must correct for the length, this is called length contraction, in the moving frame. Now, it's note with, for example, in our little, if we have like a car moving very fast, it's in this direction. Let's just draw some axes. So it's X, Y, and this is the Z direction. If it's moving along the X axis, we only see length contraction in the axis. The Y and Z dimensions will be unaffected. So you're going to have this distortion in this one direction, which makes it just quite hard to get your brain around what that would look like. When this was first postulated, the scientific community were, let's say, skeptical, and very few people thought this was actually true. However, this has now been proven by experimental results, and we're going to look at a couple of these scientific proofs of this time dilation and length contraction. So we're going to consider muons. So muons are subatomic particles, and they result when cosmic radiations impact the Earth's atmosphere. So you've got the Earth, and then out here you've got the atmosphere, and you've got cosmic radiation coming in, and it interacts with the Earth atmosphere, and you get these subatomic particles created, and one of them is muons. So the muon are unstable. They're unstable with a half-life of around 1.56 microseconds. And we've measured that in the laboratory, that you can create, in particle accelerators, muons can be created, and they've measured that they've got a half-life of 1.56 microseconds. It is possible to make high altitude measurements and count how many muons would be detected per second. Equally, the same measurements can be made at ground level. So we can measure how many muons are up in the upper atmosphere, and then we can measure them on ground level. And we can see if there is any, if special relativity has any impact on this. So imagine you are in a high altitude, you've got a high altitude laboratory in space, and like a satellite, and it's about 10 kilometers above the surface of the Earth, and we count 1 million muons. The half-life is 1.56 microseconds, and the velocity is 0.98 of the speed of light. So how many muons would you expect to hit the Earth's surface? So classically, the time would be equal to 10,000 meters over the velocity, which is 0.98 times c, which would be 34 times 10 to the minus 6 seconds, which is a lot more than the half-life. So that is around, therefore that's around 22 half-lives, and would give us, which leads to a survival rate of about 3 times 10 to the minus 7 in every million would make it, sorry, 3 times 10 to the minus 7 would make it, or 0.3 in every million. Okay. Now we can actually measure how many muons would hit the Earth's surface. We count, so observation, we observe, what do we observe? We observe 49,000 muons in every million. That is an awful lot different from 1.3, and it's so much different. You can obviously, you cannot, this is not an experimental error. If we use the Lorentz factor, special relativity, we find the Lorentz factor would be 5. So this means the time dilation would be, we would take the half-life of the muon, times it by 5, we get a half-life of 7.8 muons per second. Or we can use contraction, so the length contraction would be length over the Lorentz factor, and that would give us just, instead of the muons would observe, instead of being 10 kilometers, the muons would observe 2 kilometers, would be the length experienced by the particles. Whichever way you do, that accounts for the fact that we get the muons, so many muons hitting the surface of the Earth. And therefore we've now shown special relativity by experiment and observation. We also have fast moving clock corrections. So what happened is, in 1971, two physicists, they had atomic clocks. Now atomic clocks are highly accurate clocks, and they synchronized two of them with the US Naval Observatory. So the one clock stayed here in America, and the other clock was put into space and whizzed round the Earth, and then brought back to the same place. And we saw, when they did this, we've seen that the clock had slowed, that had been whizzing around the Earth very, very fast. Practically, GPS, global positioning satellites, must be compensated to account for relativity. So if you have satellites go round the Earth at very high speeds, and they lose round about 7,200 nanoseconds per day, which doesn't sound very much, but that will that all adds up. So they need to, when the first satellites were put into space, physicists didn't know if relativity would matter, but after about 20 days, they noticed that the GPS and were out of sync because of special relativity. So now satellites, global position satellites, have to have that relativity correction put into them so that they stay in sync with the clocks that are stationary on Earth. So I hope that helps.